Alright, so this is the notes for section 8.1 where we're going to take a look at composition of functions. Okay, so the big idea here is that the function that results from following one function by another is called the composite of two functions. The operation is called a composition. So let's first take a look at what it means to do a composite. You did some composites back in geometry. So if I have the composite of G and then this little circle and F, it basically, by definition, it just says for two functions f and g, the function maps x onto g of f of x. So in other words, we have a value, some number x, and we're going to put it into the f function, get what you get out of that, and then whatever comes out of that f function is what we're going to put in for the g function. So the domain is the set of all of the domain of f and is in the domain of g. So really what you want to do is you want to think about a composite of a function is where we're going to use two functions. We're going to put a value into one function. Whatever comes out of that function is going to go into the second function. Alright, the operation signified by the small circle is called a function deposit, or just a composite g following f, or it can be read as f followed by g, or the composite of g following f, or the composite of f then g. All of those are different ways that we might say that. Alright, so let's take a look at an example of how we can apply composites of functions. So we are given two functions. We're given the function f here, and we're also given a function g. So here's what f of x is equal to, and here's what g of x is equal to. Now what we want to do here is we want to find, first of all, what is g of f of 5? Well, we're going to start inside the parentheses. The first thing I need to figure out is what is f of 5. So I'm going to just apply what we know about functions, meaning that we're going to take 5 and put it into the function of f, putting it in for the independent variable. So I'm going to have 2 times 5 plus 3, which would be equal to 13. And then I'm going to take that 13, since that's what f of 5 is, and I'm going to be putting it in for g. So I have g of 13 is equal to, now I'm going to go to my g function, 13 squared minus 3. So when I plug 13 into my function g, I'm going to replace x with 13, and we get 169 minus 3, which would be equal to 166. Therefore, when I say what is g of f of 5, g of f of 5 is equal to 166. Now, if I do my second function, operates the same way, f following g of 3. So the first thing I'm going to do is to find g of 3. So g of 3 is, we're going to take 3 and plug it into my function. So I have 3 squared minus 3. Well, 3 squared is 9. 9 minus 3 is 6. Now I'm going to take this 6 and I'm going to put it into the function f. So into my f function. So I'm going to say f of 6 is equal to 2 times 6, plugged it in, plus 3, which would be 12 plus 3, or 15. Therefore, f following g of 3 is equal to 15. Alright, so we don't always have to find particular values when we're taking a function of a function. We can also find a new function given two functions. So let's take a look at this. If you take a look at the example, the activity in your book from your reading, it says suppose that the rebate in that activity was 1,500 and the discount was 22%. We would have two functions then. We'd have a function here, r of x, which would represent the rebate, and then we'd have a second function, d of x, which represents the discount. Okay, well, what we want to do now is, we were saying, okay, well, let's write a new equation. We'll call it p of x, which is a composite of the rebate function and the discount function, where I'm going to do the rebate of the discount function. So in other words, I'm going to take the discount first and then the rebate. And then part B, we're going to say, let's develop a new function that's the opposite. So d of r of x. Okay, and then finally we want to look at, well, what happens, in every case? Is it always true that p of x is less than q of x? So first of all, let's do part A, where we're trying to find this new function p of x, which is r of d of x. So really what I'm going to do is I'm going to take d of x, which is this 0.78. Let's get back to our pen here. This 0.78x, and I'm going to plug that in here. So anytime I see x in r of x, so like right here, I'm plugging in 0.78x. So I take x out and put in 0.78x minus 1500, because it's minus 1500. So all I've done is rewritten r of x with 0.78x in the place of x. So this would be our new function now, which we're going to call p of x. Now we can find a new function q of x kind of in the same way, but this time I'm going to put the value of r of x in for x of d. So I'm going to put x minus 1500, okay, which is this right here, in for x in this function here. So I got 0.78x, or 0.78 times x minus 1500, and if I distribute, I would get this 0.78x minus 1170. Now part C of the question says, is it true for all x that p of x is less than q of x? In other words, is it true that if I take the discount and then the rebate, that would always be less than if I take the rebate and then the discount? Okay, and let's just see if that's true. Well, if I put 0.78x minus 1170, so that would be our q of x, and we're going to subtract p of x from it. You'll notice that I always get a value, I get a value of 330, and what that tells me is that p of x is always going to be $330 less than q of x. Alright, just like functions, there's two different ways that we can write composites of functions. One is mapping notation, as we have here, and the other is function notation. Now you'll find that most of the time in class I'll use function notation. I just think it's a little bit more clear, but both of them are totally fine. Now the last thing I want to mention as it relates to that is it's really important that you understand that composites of functions are not commutative. In other words, f of g of x and g of f of x are not the same thing. Okay? Now, the last thing I want to do is I want to think about finding the domain of a composite of functions. And what you can do is you can think the domain can include only those values of x for which the first function is defined and that are paired with values that are in the domain of the second function. So we'll take an example. Let's take a look at an example of what I'm talking about here. That's a little bit confusing, but I think when you see the example, it's a little bit easier to work with. So if I have two functions, t of x is equal to 1 over x, and we also have g of x is equal to x squared minus 100. Okay, what we want to know is what is the domain of t of g. Alright, so the first thing I'm going to do is I'm going to find t following g, or t of g of x. Okay, to do that I'm going to put x squared minus 100. I'm going to put this right here, and I'm going to plug that in for x right over here in t of x. Now when I do that, I'm going to come up with this function right here. So this is the function of t of g of x. Now what I want to do is I want to think about the domain. Well, the domain would be those values where x squared minus 100 is not equal to 0, because that bottom can't be 0. So if I were to solve that, that means that x cannot be 10 or negative 10. So that would represent the domain. So it would be all real numbers except for 10 and negative 10.